Okay, so today is going to be an interesting video. We're gonna look at the Brillouin zone in 2 dimensions and by extension 3 dimensions, and we're gonna come back finally then also to resolve that problem we had from before having to do with divalent metals, right? One-dimensional analysis predicted that divalent metals would be insulators, which is of course absurd because we can measure the conductivity. These are good conductors. So we're going to see how that problem, that contradiction, gets resolved when we look at it from a 2-dimensional or 3-dimensional, preferably 3-dimensional point of view. Okay, but let's start out here in 1 dimensions quickly, just to remind ourselves of a couple of things. So I can draw the k-axis, okay, and we know that from minus pi over a to pi over a, well, that is our first Brillouin zone, we said. Okay, states that fall outside of the first Brillouin zone can be, in principle, in the reduced zone scheme, be folded into the first Brillouin zone. Okay, and so we can look at, for instance, the second Brillouin zone here. Okay, there's part of it that goes from minus 2 pi over a to minus pi over a here in blue, and then the other part from pi over a to 2 pi over a. And you notice here, for instance, that taken together, the blue area is, or the blue line segment, the width of those 2 blue line segments is equal to the width of the first Brillouin zone. So even in 1 dimension, we see that the first, second, and also third and fourth, all the Brillouin zones have the same size. Okay, so what we could do is to look at the reciprocal lattice vector G, and there's also another one here at minus G. How do we get the first Brillouin zone from those 2 reciprocal lattice vectors? Okay, well, one thing you could do is you could bisect. You could bisect the G1. Okay, and so that's what we're going to look at. Okay, take the G vector and do an orthogonal bisection, perpendicular bisection. Okay, and then that gets you to here, right? So if you take this vector and you sort of cut it in half, if you will, then you get to the boundary of the first Brillouin zone here. And similarly, if you take the minus G1 and bisect it, go to the halfway point, then you end up with the other boundary of the first Brillouin zone. So it seems like that's one way we could construct the first Brillouin zone, by looking at these reciprocal lattice vectors that, remember, encapsulate the periodicity of the atomic lattice, right? G1 is a particular vector that encapsulates or that represents the periodicity of the lattice. If we bisect that vector, we get the boundaries, one of the boundaries of the first Brillouin zone. The question then is, can we apply the same type of reasoning to 2 dimensions? Okay, so let's draw a 2-dimensional reciprocal lattice. Okay, let's consider the simplest case of a square lattice. The reciprocal lattice is also a square lattice, and here I've drawn some of the the lattice points of that reciprocal lattice. Okay, and here are some G vectors. So in other words, any vector that starts at the origin and points to one of those dots is a reciprocal lattice vector. And here I've highlighted G1 and G2, as well as their inverses. Okay, and so now let's see if we can apply this bisecting idea. Okay, let's bisect these vectors. So, okay, here we go. Here I'm bisecting G1. Here I'm bisecting G2, bisecting minus G1, bisecting minus G2. I get sort of this area that's being carved out Okay, and that area now is going to be called the first Brillouin zone. Take a moment to think about how this would work in 3 dimensions. Okay, what would it mean to bisect a vector in 3 dimensions? What you should see is that now we're going to be using a whole plane that bisects the vector in a perpendicular fashion. The perpendicular bisector would then be a plane. Okay, and then this here would sort of enclose these various bisecting planes would, hopefully, if you can see that, sort of define a volume element at the center. Okay, so you'd need another lattice vector, reciprocal lattice vector coming out at you, for instance, and going into the board as well. Okay, so that's the first Brillouin zone right there. Yeah. So here we go. Let's draw in some more G vectors. So for instance, here's 4 of them pointing to the diagonal lattice points in reciprocal space. Okay, and again, we could try to bisect these as well. Let's do that. Let's bisect these as well. Okay, and we get then these blue lines in 3-dimensional space. They would be these planes again, but here we get these lines in 2 dimensions. Okay, and so they also enclose some space here, some area. Okay, they enclose additional area. That area that is enclosed here but not already accounted for in the first Brillouin zone is what we call the second Brillouin zone. Okay, so we're talking about these corners here in blue, okay, that are enclosed by these bisecting lines here, okay, and this blue area is the area that's enclosed by those bisecting lines that is not already in the first Brillouin zone here in pink. Okay, we can we can do something similar with the 3rd and 4th Brillouin zones as well, and there is an exercise on the homework where you can practice a little bit drawing those higher order Brillouin zones. Okay, so another way to phrase the whole thing is the following. We can say that the first Brillouin zone is the area that's closest to the origin, namely k is equal to 0. So any point in this zone can be reached from the origin without having to cross any bisecting lines. You see that we don't have to cross any bisecting lines if we stay within the first Brillouin zone. Okay, so what about the second Brillouin zone? The second Brillouin zone are all the points in reciprocal space that can be reached from the origin by crossing no fewer than 1 bisecting line. Okay, these bisecting lines in 3 dimensions are often also referred to as Bragg planes. We've already encountered the Bragg condition. These bisecting planes in 3 dimensions are sometimes also referred to as Bragg planes. So in 3 dimensions, then this definition would read: the second Brillouin zone, which is a volume, are all the points in reciprocal space, 3-dimensional space, that can be reached from the origin by crossing exactly 1 Bragg plane, or no fewer than 1. Okay, so this keeps on going with the 3rd, 4th, and so on Brillouin zone. All right, so that's another kind of nice definition, working definition for these Brillouin zones. So far so good, you might say, but why are we doing this? What is it really good for? What is it doing for us? And that's always a fair question in physics. So we have to go back to the electrons themselves that we're trying to model here and their energy bands. We have to make that connection. Okay, and so remember that from a 1D point of view, when we hit any of those boundaries, those Bragg planes, if you will, or Bragg lines, or bisecting lines, just all different terminology for the same thing. When we hit one of those, then there is a discontinuity in energy, right? There we have a gap, an energy gap then. So when we hit the boundary of the first Brillouin zone, for instance, in one dimension, that's just a point pi over a and minus pi over a. When we go along the k-axis, okay, and hit one of those special points, namely the boundaries of the first Brillouin zone, then we get these gaps opening up in the energy band, in the energy sort of profile. Okay, and so this is, right here, for instance, is what I'm talking about, right? So we have these two. This is my first Brillouin zone, and at the boundary, in the bulk of it, everything is copacetic, but as soon as you reach the boundary, then you get these gaps. And so that's now going to also carry over into higher dimensions. Okay, so here's my first Brillouin zone, hatched here, the hatched area. Okay, and then what I can do is I can go in any direction, but when I meet that boundaries, I should see a gap, right? That's what we're saying. So here, for instance, if I go to the right in K space, then as soon as I hit pi over a, I should see that energy gap. Okay, here I'm using the extended zone scheme. I'm going to go past pi over a, but there's a gap there. Okay, so similarly, I could go vertically in K space, and when I hit pi over a on my journey, this is the blue line now, the blue dashed line. I'm marching up in K space, and when I hit that boundary at pi over a, again, I should get a gap. Now, I can also, of course, go diagonally. Here's the purple path. I can start from the origin and sort of head in a diagonal direction in a 45-degree line here, and I'm going to reach the boundary right here. So what would that look like? Well, really not much different, okay? When I hit that boundary, I should get a gap. Now, where is that boundary, though? My path is longer here, right? As a matter of fact, I wouldn't encounter it until a distance of square root of 2 times pi over a away from the origin. Okay, and so the dotted line that I now have to draw in an EK diagram, an energy versus wave number diagram, while that boundary would sit right here at square root of 2 times pi over a, not at pi over a as before. Okay, and so I basically I'm going to more or less stay parabolic until I hit that boundary. Okay, so something like that. Okay, so I would get some kind of energy slice like this. Okay. Now, why don't we take the red curve and sort of superimpose it on the purple curve? Okay, why not? All right, let's do that. Okay, so here is what I got for the X and Y direction. Now I'm using the reduced zone scheme again, so I'm not continuing past pi over a, but reflecting. Okay, and so that is the scenario that when you go horizontally or vertically. And now, what about when I go at a 45-degree angle? Well, here's my axis, my 45-degree axis, okay? And here is then where I encounter the boundary for the first Brillouin zone. And so I would basically extend this parabola a little bit higher, and then I have to come in horizontally to meet that boundary. Okay, and then there would be a gap, and there would be the second band up here. Okay, so that's kind of interesting, but why am I making a big deal about it? Okay. Okay, well, first off, there are these bits here that are associated with the second Brillouin zone, or we could say the second band. Okay, so notice though, here's an important point. Some parts of the second Brillouin zone now folded into the first Brillouin zone. Some parts of these branches here, some part of this branch in particular here is lower in energy than other parts that still fall within the first Brillouin zone. Okay. For instance, compare these three states here to those three states there. You have to conclude that these ones here are lower in energy than those ones there. This one here is associated with the second Brillouin zone. Okay, this is the second Brillouin zone in the reduced zone scheme. Okay, but this is still the first Brillouin zone. Okay, sort of near the corner of that zone. Okay, so the question then to you is, which states would you fill with electrons first? So if you had to start now populating this crystal with electrons, okay, which ones would you occupy first? As you're filling this up, which states would get occupied by electrons first? Okay, think about this question for a moment. You should have answered that these ones get filled up first because they're lower in energy. Okay, we always want to minimize our overall energy with our arrangement of electrons, and so I would fill these ones before I would fill those. Okay, so the conclusion then is that parts of the second band, or we could say parts of the second Brillouin zone in the extended zone scheme, second Brillouin zone, will be filled before the entirety of the first band in the reduced zone scheme, or the first Brillouin zone in the extended zone scheme is filled with electrons. Okay, that was a mouthful. Let me say it again. Parts of the second band will be filled before the entirety of the first band is filled with electrons. So this is unusual, right? We didn't get that in one dimension. We now see that in two dimensions, though, that is indeed the case. But I want to show you another way of looking at that. Okay, there's another way to see the same thing. And here we look at the 2D extended zone scheme. Okay, so here is our second Brillouin zone here in yellow. The first one falls within that green square, and the second one then are those corners. Okay, so the free electron, okay, for a moment, its energy is given by h bar squared over 2m times k squared. But here, of course, we're in two dimensions, and so k is a vector. Okay, and so what I really have to say is that the energy of a free electron is given by h bar squared over 2m times the magnitude of that vector squared, of that k vector. Okay, so I can say that, for instance, if I draw a circle centered around the origin in reciprocal space, okay, and that that circle then represents all the points in reciprocal space that have the same energy. I think about why that is. Okay. Why is that? When you think about it a little bit, you conclude that any k vector that whose tip ends up on that circle has the same magnitude, right? And therefore then the magnitude squared of those k vectors are all the same, and therefore the energy of the associated electron has to be the same anywhere on that circle. Right, so this k magnitude, the magnitude of that vector is constant everywhere on all points on that circle. Okay, so here's another circle. Okay, and so I tried to draw a concentric circle of a larger radius. And again, all points in k space that lie on that circle would have the same energy, now a larger energy. Okay, and then here is another circle. Okay, and again, for the free electrons, we would conclude that all the states represented by that purple circle would have the same energy. Now, why did I draw that purple circle? Well, that circle, I've drawn it here such that it has the same area as the first Brillouin zone. I'm not sure if I was entirely successful there, but that's what I was going for. I selected the radius of that circle such that the area of that circle would have the same area, that circle would have the same area as the square, the green square. Okay, so the green square is the first Brillouin zone. I wanted a circle that has that same area. Okay, so that's the first thing. And the second thing to then realize is that this purple circle encloses most of the first Brillouin zone, but also parts of the second Brillouin zone. Right, so there are some parts here of the second Brillouin zone that are part of the interior of that circle. Then there's also parts of the first Brillouin zone that fall outside of that circle as well. Okay, so couple reasons why we're looking at this. First, we could say that this purple circle encloses all states of an energy less than some threshold energy, call it E naught, right? Where E naught is h bar squared over 2m times the radius squared of that circle, k naught squared. Okay, so all states that have an energy less than E naught will fall within the interior of that circle, the area of that circle. Okay, so that's one thing to realize. And the second thing is that since that circle has an area equal to that of the first Brillouin zone, namely an area of 2 pi over a squared, it also then encloses the same number of states as are located within the first Brillouin zone. Okay, so it sort of has the same number of states as the first band has. And so that's interesting. Okay, same number of states. So we know that the first Brillouin zone in one dimension has an occupancy, well, has n, capital N, a number of distinct states, and an occupancy, sort of a maximum occupancy of electrons of 2 times n, capital N, n being the number of ions. Okay, so similar here as well. Okay. But what we're saying is that this purple circle basically encloses the same number of states. Okay, so here we go again. Now I'm going to shade in some interesting parts here. Okay, so the red here, what does that represent? Well, you guessed it, it's the second Brillouin zone electron occupation, right? So those are the regions that really fall into the second Brillouin zones that will still be filled up with electrons. Okay, and then we have these blue corners here. And what does it represent? Well, you can see that it falls outside of that circle, that purple circle, and therefore those are the parts of the first Brillouin zone that are left unoccupied. Right, so I'm going to fill in electrons up to a certain energy, E naught, thereby I'm going to cover the interior of that purple circle. Okay, everything in the interior of that purple circle is occupied with electrons because I'm filling up electrons up to a certain energy. Okay, and what that means then is that these regions will be filled, but they fall into the second Brillouin zone, and these regions here in blue will remain unoccupied, but they fall into the first Brillouin zone. Now, if I had drawn this perfectly accurately, then we would have to say that the red and the blue regions should be of equal area, of course, because remember, we said that I wanted to draw a circle that had the same area as the first Brillouin zone, right? So whatever area I'm missing here, I got to make it up here. Whatever area I'm missing here, I got to make it up here, and so on. So if I had drawn this exactly precisely, and it doesn't look like maybe the areas will be exactly identical, maybe I've overdrawn, I've exaggerated a little bit the size of that circle. Maybe I should shrink it just down by a little bit, but more or less equal. Okay. Now, we can look at this whole thing from also a reduced zone scheme point of view. Here's my purple circle again. Okay, there's my first Brillouin zone in green. So this here, I can, if you want to think in terms of shifts, I could shift this by 2 pi over a in the y direction. I would end up here with this. I can shift this and I end up with that, and so on. I can shift this over and I end up with that. So these red line segments here now indicate the boundaries once I've shifted, right? I folded things back into the first Brillouin zone. Things that normally would fall outside of the first Brillouin zone into the second Brillouin zone can be folded back in to the first Brillouin zone in the reduced zone scheme. That's what we do, right? In the end, we only want to look at the first Brillouin zone, and the price we pay is we have energy bands. We have, right? Anything that used to fall outside the first Brillouin zone now gets folded in and then becomes the second, third, fourth bands within the first Brillouin zone in this reduced zone scheme. Okay, and so let me now erase everything that's outside of the first Brillouin zone. Okay, so we really just don't care what's outside. We're focusing on the first Brillouin zone, but we have these the second band here in red, right? So we have the filled part of the second band in the reduced zone scheme here in red, okay? And then here in this picture, we have the filled part of the first band in the reduced zone scheme. So this is the filled part of the first band. Notice that there are some empty parts here in the corner. In the corners, these are the empty part of the first band. This here is the filled part of the first band. And then here is the filled part of the second band. So far, so good. You might have to stop the video here and see and take it all in. There's a lot of information here to contemplate and to absorb, okay? So feel free to pause and sort of reflect on some of these ideas. Okay. So again, I can sort of go into different directions. So for instance, I can go here along the case of x-axis, and here I can go sort of in a diagonal direction. Okay. And so now let me plot sort of an energy diagram. Okay, so there's nothing strange here. Okay, if I go in this direction, okay, here's my first band, and then here's my second band folded in, right, in the reduced zone scheme. What about if I go in the diagonal direction? What happens there? Well, similar thing, right? So I wouldn't really get to the edge of the the zone until I cross square root of 2 pi over a, and then things would get folded back in. Okay, so now I'm going to start filling up electrons up to a certain energy E naught, here indicated by the red dashed line. So I'm going to start looking at everything, every state that has an energy below the red dotted line or the red dashed line here at E naught. Which states would I actually start filling? Well, you see that I would fill everything here, okay? But then this little bit here would be unoccupied. Okay? And over here in the second band, I wouldn't really fill up anything from 0 up to a certain point here, and then I would start filling. So you see that right around pi over a, I would start filling up the second band. These are those couple of states here, and then the rest would be unoccupied. All right, so if you had to do a sort of, yeah, you could say that the purple parts of these bands would be empty, whereas the brown dots would be filled. Okay, you could say that this little bit here corresponds to these red regions here, okay, that are filled, and those empty parts of the first Brillouin zone correspond to these empty corners. Okay. So this is a busy slide here. Again, feel free to pause and reflect a little bit. Okay, so I think we've got everything assembled together now in order for us to tackle this question finally. Why are divalent metals good conductors of electricity? I think we've got all the pieces assembled, and now we can bring them to bear here. In divalent metals, just as a reminder, we have 2 capital N electrons to accommodate, where N is the number of ions. So we need an area in 2 dimensions, or a volume in 3 dimensions, equivalent to the first Brillouin zone, whose states are all occupied. We need an area or a volume equivalent to the first Brillouin zone to accommodate them all. Remember that from 1D? The entire first band was filled for these divalent metals. That's why we initially concluded in 1 dimensions that they would be insulators. Okay, but what does the picture look like in 2 and 3 dimensions? Well, we still need an area or a volume that's equivalent to the first Brillouin zone. Why? Because that area or volume would enclose that number of states that I need to accommodate the 2n electrons. Okay. So how are we going to fill up which states are we actually going to occupy? Well, we said we're going to fill up most of the first band, but not the corners. Okay, so not all of it. And we fill up some parts of the second band. But certainly there, again, most of the second band is empty. Some of the second band is filled. Okay, and so the upshot now is that we have 2 partially filled bands. The first band is not fully filled because energetically it's better to shift some of those electrons that would have filled up the first band into the second band, because we could lower the energy there. Okay, and so we have a first band that is not fully filled, okay, only partially filled, and then we have a second band that is partially filled as well. So we have 2 partially filled bands, and that should make for a good conductor, right? Because partially filled bands allow for electrons to conduct, right? So from the reasoning that we engaged in before, we can say that, hey, now we have two partially filled bands, and therefore conduction is not a problem. As a matter of fact, we get conduction in the first band and conduction in the second band. Okay, all right. Thank you.